Temperature now and catalyst, okay, both of them, all right? Now I need you to pay attention. I don't want to have to start this video again, all right? Okay, first of all, we've already talked about how it affects, and I'm going to apply this the same way as I did to the other stuff that we've already been doing. For example, concentration is probably the easiest. So if I have a guy like A plus B yields C, whatever A, B, and C are, if I add A, it's going forward because it's going to try to get rid of it. If I add B, it's going to go forward. If I add C, it's going to go reverse to get rid of him. If I remove A, which way is he going to go? Reverse. Okay, in other words, it's going to be reactant favored as opposed to product favored. It's going to be favored reverse. Okay. Well, I'm going to treat temperature like one of those guys, like one of A, B, and C, like one of the guys in the equation. You say, how can you do that? Well, you'll see in a little bit. Well, first of all, it depends on, obviously, for temperature, whether energy is given off or released. So it depends on the enthalpy of the reaction. Okay, now that means we got to refresh our memory back to what? Thermodynamics chapter, right? By the way, you know what's coming up soon? I'm going to be taping again tomorrow because I've added something else from thermodynamics that applies to equilibrium. Delta G, Gibbs free energy, and how it's related to K as well. So we're going to be doing that soon as well. So a lot of this stuff, none of it goes away. Not just because you're going to have to take an AP test on it. It doesn't go away because it's often used in the next chapter. Okay. Equilibrium shifts depending on the reaction, on the enthalpy of the reaction. And basically there are two possibilities. I can either increase or decrease the temperature. Let's talk about what happens in both of those cases. But of course I have to apply it in a generic sense. If an increase or a decrease in temperature, it has to also be applied to an enthalpy being positive or negative, endo or exothermic. So let's see if we can figure this out, okay? If I have a guy let's just draw a picture first so you have an idea. If I have like A plus B yields C plus energy, what kind of a reaction would that be? Endo or exothermic? Exo, it's giving off energy. So if I were to increase the temperature of a guy like that, where's energy? Well, it's just like adding C. If I were adding C, I would force it this way, right? Well, I'm adding energy. Which way is it going to be going? It's going to be going reverse. By the way, this may surprise you, but you actually saw the same exact thing back in Chem 1. Again, Emily asked before, how come this was so hard back then? Like when we were doing liquid plus energy yields vapor. Remember this?
Yeah.
And the crazy part about this was, it wasn't that hard. All right. Matter of fact, this one in particular was fairly easy because we all have common knowledge of this stuff. We heat up liquid water all the time. We put it on the stove. We cool liquid water down all the time. Put it in the freezer. All right. So we know which way it's going to go. But I was trying to get across to you back then how it's like a balance. Like there's your one side of the balance and the other, and it's in balance. It's at equilibrium. If I increase the temperature, if I put my water on the stove, obviously I know it's going to favor evaporation. Why? Because I've made this side too heavy. I've increased the amount of energy, and it's going to favor the forward. So that's basically how this works for chemicals as well. A chemical reaction as well. It's going to favor the direction that consumes energy. It's going to get rid of that extra energy you added to it. It's going to favor that direction that gets rid of that energy, consumes it. Okay? And of course, by the temperature decrease, what's going to happen? It's like removing energy from the system. It's going to try to replace it. It's going to favor the side that produces energy. Now, I've actually can ask this. Really, I have 3 ways I'm going to ask it up here. But really, there are 4. And for each of those different ways I could ask it, I could say whether it's going to increase or decrease the temperature. So that's 8 possibilities. All right? And as I said 100 times, and one of the things I don't like about the AP exam is that there's so much that they require to memorize. Don't make yourself memorize even more. I've been working on, by the way, just recently, I'll have it probably done by the end of this week, a sheet, or actually multiple sheets, probably about 6 sheets of stuff you have to memorize. Solubility rules, colors of ions, crap like that. Don't make this one of those things. This is not about memorization. You don't want to memorize 8 different things. You want to understand Le Chatelier's principle and apply it to this concept. So let me show you the 3 possibilities. All right? Let's say I've got That guy right here. The one way I could ask it, there's really four, but there's one way I could ask it is by putting the energy right into the equation like that. It could be on either side, of course, but in this case, it's on the right-hand side. We all know what that means. That means it's an exothermic reaction. Energy is being given off. If I gave you the question like that, and I said, what would happen if I increase the temperature of this equilibrium system? What would you tell me is going to happen? It's going to favor the forward or the reverse direction? Everybody agrees. It's going to favor the reverse or favor the reactants. Good. Because it wants to get rid of this extra. Just pretend, if I said I added C, it's going to favor the reverse. Same reason. Good enough. I said there are at least four ways I could ask this question. Let me show you another way. In this case, I gave you the entire equation, and I put the energy in there. What if I said this? I gave you the equation, and I told you the delta H of the reaction. Yes, you have to remember from thermodynamics what negative and positive delta H's mean. Do you remember? What does the positive delta H mean? Endo or exothermic? Yeah, it's amazing how quickly we forget. It's endo. It's exactly right. So if he's endothermic, where does that 45.9 kilojoules go? He actually goes on the left-hand side, doesn't he? Remember? You're adding that much energy to it to make the reaction go. In that case, increase in the temperature is going to favor the forward. Okay. I said there were three ways. That's two. There's actually four. Here's another way I could ask it. I could write the whole reaction down and just tell you in the sentence or in the paragraph above, often happens in these AP questions, that this is an exothermic reaction. Just mention it as if it's in passing. Well, it's kind of important to know it's exothermic. Now let me ask you a different way, though. Let's say I decrease the temperature of this guy. I want you to think about this. I decrease the temperature. It's an exothermic reaction. It's like having energy on this side. I'm removing energy from this side. Which way is going to be favored? Forward. Right. It's going to favor the forward. And finally, I don't have another one up here because I don't think it's necessary. The last way I could ask this question is besides putting the energy right there, telling you the delta H, or saying it's exo or endothermic, I could just say energy was released or energy was absorbed. Somewhere in the process of that big, long question. You know how their questions are. You can see them from this book. How they are ugly questions with lots of extraneous information. It's easy to get lost in there. Somewhere along the line it said, well, it got cold or energy was absorbed or whatever. That will be a hint that it's an endo or exothermic reaction, and we'd use that to figure out how the equilibrium would be shifted. All right, good enough. Now, here's the crazy part that I had to add on to this from this year. That would have been the end. If you were to look at the video which I'm going to replace from last year, this year, I would have stopped there and went on to catalyst. But as I was going over some example problems, I was realized that some of the AP questions ask you how is Kc itself affected by temperature change. And I needed to talk about that for a little bit. Because in reality, I never really thought of it this way, but it's true. As I looked up stuff on this and realized I needed to teach this to you, it's really crazy what's going on here. It's not what you think. It makes complete sense. Again, don't draw this. It makes complete sense that if I say I increase the concentration of C, for example, it's going to favor the reverse direction. Why? Well, let's just think about that. Q is equal to K at equilibrium, right? If I increase the concentration of C, what have I done to Q? Q is now what?
Less.
Products are in the top, right? Remember, both of these are Kf over Kr, correct?
Yeah.
Right? So if products over reactants, Kf over Kr, products over reactants, I've increased him, I've made Q too big, correct? So if Q's too big, it has to become Kc. I've changed Q by doing that. I'm going to have to favor the reverse to bring that numerator back down to where it's supposed to be. That all makes sense. Here's the crazy part about Kc. Q isn't changed. When I change the temperature, did I increase the concentration of anybody? No. So Q is basically the same. What I've done is I've changed K. Kc changes. And then Q has to catch up to it. It's the exact opposite of what happens when you have volume, pressure, and temp and concentration changes. They actually change Q. Therefore, you got to get to K. K changes with temperature. And Q has to catch up to him. And that makes it tough. Because if you think about it, how would K be affected? It's ugly to think in your head backwards, but that's what you've got to do. If it's an exothermic reaction, Kc, for an exothermic reaction, will decrease if you increase the temperature. So you say, well, wait a minute. This is blowing my mind. Well, let's look at an exothermic reaction and see what I'm talking about here. Okay, A plus B yields C plus energy. We're all in agreement as to what's going to happen here, correct? Who's going to be favored if I increase the temperature? If I increase the temperature, who's favored? Reverse. Everybody agree it's going to be reversed. I've made this guy too heavy. It's going to go that way. You have to think about this. Remember, it's Kc and Q again. Q and Kc. I did not change Q, but I must have decreased K, right? K must have been decreased. Remember, it's Kf over Kr, right? Kf over Kr. Q is over here. K must have been decreased such that I will have to favor the reverse direction to bring Q back down. In other words, getting rid of some of that numerator over in Q. It's weird. And I know it's hard to really think that way because all the other times we're thinking about how do we get to K? You know, but now we're having to think the opposite. How did we change K such that we have to get Q into K? All right, that's kind of ugly. Anyway, another way, of course, to look at it is if it's an endothermic reaction. Kc is going to have to have increased. That's why Q will say, "Hey, I got to get this guy to go forward. I want to make that numerator bigger to catch up to K, who's now bigger." So I got to get more products. Products is in the numerator. Yeah, it's ugly. I know. Thinking about it backwards. Thinking about it both ways. I understand it. And you can see why this would be a concept that I would have left off from the beginning. Left out from like Chem 2 before it was AP. It really doesn't change your ability to be able to do those other problems. It simply makes you understand it from all sides. And of course, it's a very difficult concept to, I think, to get across. But here it is in words. Copy this all now. In words, in effect, the temperature change doesn't affect Q. Since the concentrations are not directly changed, they eventually will be changed, but they're not directly changed by you changing the temperature. What you did is you changed K. And therefore, Q has to respond to that to become K again. So when it asks this kind of a question, if it asks what this guy does, in an exothermic reaction or an endothermic reaction, if you increase the temperature, what happens to K? I know, you should be able to figure it out. I don't want you to just have to memorize that. You should be able to figure it out. You do know the answer to which way it's going to be favored. Just apply that to what must have happened to K in order for Q to be doing that, or saying that he's going to go one way or the other. I know that's tough. Because there's so much to memorize. When you see the garbage, you've got to memorize. All the colors of the ions, all the polyatomic ions we've been using all year. Now, you know some of them just from use. You know nitrate probably. You know sulfate probably. And you know some of those, even the colors that we've used, like some of the solutions that are going to be blue, copper, green, yellow, iron, and different charges of those even sometimes. For example, iron can be red, or it could be yellowish green. Well, you got to memorize that garbage. You don't need to memorize this. This is all thinking. If you understand it, you can figure it out. Just saying. All right, well, the good news is the last thing I got to tell you, the last factor that affects equilibrium is the easiest, thank God. Because, we've had enough trouble with all these. There are no math problems with this last one. As a matter of fact, all that homework tonight is about volume, pressure, temperature changes. It really doesn't even talk about this last one because it's so easy. Watch. I got that copy? Okay. The last one is what happens if I add a catalyst to the reaction. And the good news is, survey says, the catalyst doesn't shift equilibrium. Wow, that's nice. Okay, so am I just going to put your pens down? Not quite. A couple things to say about this. The reason it doesn't shift equilibrium, I'll tell you first. And then what does it do? If it doesn't shift equilibrium, it still does some small effect on equilibrium. What do you think it would be? What would the small effect be? It speeds it up. Exactly. It gets it to equilibrium faster. Some of these reactions take a long time to get to equilibrium. The ones we've done, like the ones we use the KC for the iron thiocyanate one, that guy, instantaneously turned red, okay, and it was done. Other equilibrium reactions may take days, hours, minutes, whatever, okay? So, first off, why does it work? Why does it not affect equilibrium as far as shifting it either way? Well, you think about it. Doesn't it lower the activation energy for both directions an equal amount? Absolutely. Let's take a look at that. You don't need to draw this because you've seen this reaction graph 100 times, but here it is. Energy versus time. Let's take an exothermic reaction. If I have a catalyst, the path might look something like that, where I've lowered the activation energy. Well, the thing is, it's lowered it for the reverse direction the same amount as it's lowered for the forward direction. That's the same amount. So it makes no difference. It's going to not shift the amount you have at the end. It's simply going to make it reach equilibrium faster. That's basically the key. Okay? So increases the rate of both reactions the same amount, so it reaches equilibrium more quickly. And that's all you really need to know about a catalyst. All of these concepts, by the way, this is the first and longest chapter on equilibrium. We have 2 more chapters we're going to do. They are much shorter. They're about half the length of this one. Because we're getting all the concepts. How do you apply all the stuff about Le Chatelier's principle and stuff? Well, you're going to use these same concepts in the chapter on Ka and Kb. That's acid-base equilibrium. You're going to use the same concepts on solubility equilibrium. Okay? That's why this one's taking so long.
We don't learn we have to learn the concepts.
We have to learn all this stuff. It's going to be the longest test, too. There are 2 tests I think I might actually fit into one period, which I haven't been able to do lately. All right, good enough. You bring out that copy? All right.